Hi everyone, welcome back. We're now going to go into part 2 of planar graphs. In this lecture, we're going to get into some properties that planar graphs have to have. And this is going to allow us to show certain graphs cannot be planar. Because if all planar graphs have to have certain properties, then if we can show a given graph doesn't have the property that all planar graphs have, then it can't be planar. And this is how we're going to show that K5 and K33 are not planar. The other thing we're going to do is we're going to finish off with an application of these ideas to show that there are exactly 5 platonic solids. So that'll be an interesting little application of these ideas. So just as a brief review of terminology that we introduced last day, suppose we have a planar embedding of a graph. So we'll just work with an example here. We've got a planar embedding of a graph. So the ideas here are always going to be, from this point forward, we're assuming our graphs are planar, so that we can draw planar embeddings, we can talk about faces and all of that, because faces only make sense for planar graphs. So I've got a planar embedding, and from this planar embedding, it divides this space up into regions, and let's label our regions. We called them faces, F1, F2, and F3. How do we know there's going to be 3 regions no matter how we draw this planar graph? Well, that's Euler's formula. Euler's formula tells us, based on the number of vertices and edges, we expect that any drawing of the graph is going to have precisely 3 faces. So in this case, it's the number of vertices minus the number of edges plus the number of faces. We've got vertices are 6 of them. We can actually label them. 1, 2, 3, 4, 5, 6. The number of edges, there are 1, 2, 3, 4, 5, 6, 7 of those. And the number of faces is 3, and that adds up to the value of 2. So that's just a quick review of Euler's formula and to check that it holds in this example. Now, what about facial walks? We introduced these last day as well. These are going to be quite an important topic for today. Most of our discussion is going to be related some way to facial walks. So what is a facial walk? Well, let's consider face F3. A facial walk is that shortest walk around the edges and vertices that bound that face. So if we start at 4, let's say, then our facial walk looks like that. So we can jot that one down. It's going to, we'll start it at 4. We can start it at any vertex because it is going to be a closed walk. We'll come back and close in on itself. So if we start at 4, we went to vertex 3, then 5, then 6, then 1, then 2, then 3, and then back to 4 again. The length of our facial walk, in this case it is, we can count it again just by going along it. 1, 2, 3, 4, 5, 6, 7 edges we've used. Or we can also get that same count by just counting the number of hyphens here, because I use these to denote the edges rather than labeling the edges and writing down their labels there. So we get the length is 7. One thing to note is that this walk is not a cycle or circuit because it repeats an edge. In this case, it's edge 3, 4. So because it repeats an edge, it can't be a circuit, and all cycles are circuits. So because it's not a circuit, it can't be a cycle either. Okay, so that was a quick review of some of the terminology we introduced last day. What we're now going to introduce is this idea of a face degree. So a face degree in a planar embedding of a graph is just defined to be the number of edges of the facial walk. So let's look at those examples that we just did up above. We'll redraw our planar embedding, our labels. 1, 2, 3, 4, 5, and 6. And now we're interested in the degrees of these faces. And by definition, it's just the length of the facial walk. So if we want to look at what the degree of F1 is, what is the length of the facial walk around that face? It's of length 3. There's a triangle that goes around there, so it's length 3. How about degree of f2? Well, what's the length of the facial walk that goes around it? It's of length 4. It uses 4 edges. And the degree of the face f3, well, we already worked that out above. We found the facial walk. We can count it again. 1, 2, 3, 4, 5, 6, 7. So it's degree 7. One thing to be aware of, though, is that there are multiple ways to embed this graph as a planar embedding, and that will change how these degrees of the faces work out. It's not going to change the number of faces. The number of faces is always going to be 3 no matter how we draw this graph as a planar embedding. That's what Euler's formula tells us. The number of faces is fixed, depends on the number of vertices in the edges, and in this case it's 3. So we're always going to get 3 faces, but the degrees of those faces may change depending on how we draw the embedding. So note, different planar embeddings may give different degrees. And so let's have a look. We'll draw a different planar embedding. And I'm just going to change this ever so slightly. Rather than have that last edge stick out, I'm going to make it go in. It's the same graph, 1, 2, 3, 4, 5, 6. The only thing I did was just drew it in a different way. It's still a planar embedding. I still have 3 faces, f1, f2, and an infinite face f3. The only thing that's changed now is that the degrees of these faces may be different. And so let's jot down what these degrees are in this case. Degree f of f1, that's still 3. There's still a triangle that goes around it. How about f2? Well, I'll wander around f2. 1 edge, 2 edge, come back along it. That's 3, 4, 5, 6. So that now has degree 6 because the walk around f2 has length 6. And what about f3? Well, that's 1, 2, 3, 4, 5. The walk around f3 has length 5, so it's got degree 5. So the degrees have changed. Okay, so this could be problematic if the degrees depend on the embedding. Then I have to worry about if I'm going to make statements about a general property of an embedding. It's going to be hard to talk about it in this way unless there is something that remains invariant, that doesn't change. And there is. Let's look at the sum of the degrees of these faces as they run over all of the faces in the embedding. And so in this case, this is the degree of f1 plus the degree of f2 plus the degree of f3. That's 3 plus 4 plus 7, or 14. If we do the same sum over here, add up these values, 3 plus 6 plus 5, also 14. So it seems that even though the degrees change, the sum remains the same. What is so special about this number 14? Well, that's actually just twice the number of edges. And it's no surprise that that's going to come up here, because if we think about how we computed these degrees, how did we do it? Well, we just wandered around the edges that bounded that region, and we just counted up how many we hit. So for an edge like this one here, 5, 6, it gets counted once when I do the degree of f2, but it also gets counted once when I do the degree of f3, because f2 is on one side of the edge, f3 is on the other side. So that edge, 5, 6, gets counted once in the degree that's on one side of the edge, the face that's on one side of it, and it gets counted in the degree of the face that's on the other side of it. But to contrast that, this edge like 3, 4, it has the same face on either side, but it actually gets counted twice, because the way we did it was we came along, went out along the edge, and then came back along the edge. And so we see that every edge contributes a count of 2 to the sum of the degrees. And therefore, we will get that the sum of the degrees is always twice the number of edges. That's worth noting as a theorem. So if G is a multigraph embedded in the plane, and F1 through Fk are the faces, then if we sum over all the degrees, we get exactly twice the number of edges. What is our proof? Well, our proof is exactly what we just stated on the last slide. Each edge is counted twice in the sum. Once for each face on either side. And so a picture of this could be, if our edge E was part of a facial walk that looked like this, then it would get counted in the degree of Fi. It would also get counted in the degree of Fj. Or our edge could look something like this, where a facial walk could be, go around, and then along edge E, and then around another part of the walk, and then back along edge E to finish up. In this case, it gets counted twice when we work out the degree of Fi. Or we could be in a situation where edge E is a loop, in which case it's getting counted once as a part of the degree of Fi and once as a part of the degree of Fj. So just a couple of pictures to sort of support our sentence above that says that each edge is counted twice in the sum. So this is another degree sum formula. We already had that the sum of the degrees of the vertices in a graph is equal to twice the number of edges. Now for planar graphs, we get this other degree sum formula. The sum of the degrees of the faces is twice the number of edges. And those two degree sum formulas working together are going to allow us to get a number of results about planar graphs. And so this leads us now to properties that planar graphs have to have. And I'm going to phrase it as, what is the maximum number of edges a planar graph can have? Notice I've added the word simple there just to emphasize we are talking about simple graphs. In other words, no loops, no parallel edges. So we just want to focus our attention on non-multigraphs, so just graphs. But to put the emphasis there, I've added the word simple, just to emphasize in your mind that there are no loops, there are no parallel edges. What is the maximum number of edges such a planar graph can have? Well, the idea is that in order to be planar, you can't have too many edges. If you have too many edges, then you just can't fit them all in a planar graph. Why are we avoiding the multigraph case? Because it doesn't really happen in the multigraph case. I can just add as many edges as I want, and I can be planar. So there really isn't, and then I can also add loops and loops and loops. So we're not going to be able to get an edge bound on multigraphs. But if I avoid the situation where I'm allowing parallel edges and loops, then I can get a bound. There can't be too many edges. And that's what this first theorem says. You can't have too many edges. In fact, the number of edges in your graph cannot exceed 3 times the number of vertices minus 6. So that's the first thing we're going to prove. So let's go ahead and do that. Since G is and again, I'll write the word simple here, is a graph, in other words, not a multigraph, then each cycle has length at least 3. We won't have cycles of length 1 or 2. So each cycle has length at least 3. Therefore, a facial walk has length greater than or equal to 3. And this uses the fact that the number of vertices is at least 3. So because we're in a simple graph, each cycle has length at least 3. And so a facial walk going around a face is going to have length at least 3. The one thing we have to avoid is, what if we got a facial walk by just going out to a vertex and coming back? Well, in order for that to be a facial walk, this graph has to consist exactly of these 2 vertices with that one edge, and we are avoiding that situation. We want our vertex set to have at least 3 elements in it. Okay, so that means So therefore, the degree of a face is at least 3 for all faces in our graph. All right, so that's this first step about if it's a simple graph, then we know some information about the length of the facial walks. In fact, they have to be of length at least 3, and therefore we get this degree result. So by the previous theorem, theorem 6.3.3, we have that twice the number of edges is the sum over all of the faces, their degrees. But we know that each of those is greater than or equal to 3. So this is greater than or equal to 3 times the number of faces. And that's worth noting that we've now proven that part. We got that second part of the conclusion of our theorem, that 2 times the size of the edge set is greater than or equal to 3 times the size of the face set. What else do we have? Now, by Euler's formula, we have that 2 is equal to the size of the vertex set minus the size of the edge set plus the size of the face set. And we can now write this as V minus E. And then what is F? Well, this result tells us that F is less than or equal to 2/3 of E. So that's worth noting. So F is less than or equal to 2/3 of E. So that means that we can write this as less than or equal to, and we can put that 2/3 of E there. And so that becomes then 2 is less than or equal to V minus E plus 2/3 of E, that's minus 1/3 of E, the size of the edge set. And then we can go ahead and solve for the number of edges in this inequality. So I'll move the edges to the left-hand side. They come over as a 1/3 E. I'll move the 2 to the other side. That gets as a V minus 2, and then I'll multiply through by 3, and I get that it's 3V minus 6. And there is the result we wanted. The size of the edge set is at most 3 times the number of vertices minus 6. And it followed from the degree sum formula for the degree of the faces and Euler's formula. So those two things brought together, those two properties of planar graphs brought together, gives us this property of planar graphs. And that's in the case where we have 3 or more vertices in our graph. So what this is telling us, the takeaway from this is, if a graph is planar and it's got 3 or more vertices, then it can't have too many edges. The number of edges cannot exceed 3 times the number of vertices minus 6. If it's got too many edges, it just can't be planar. We can't fit it in the plane. So here's our first result that follows from that theorem, and that is the graph K5 is not planar. Why is that? Well, for K5, we have the size of the vertex set is 5. The size of the edge set is 5 choose 2, or 10. And so, what is 3 times V minus 6? Well, that would be 3 times 5 minus 6, or 15 minus 6, or 9. So this is the most number of edges we can have on a graph with 5 vertices so that the graph is still possibly planar. We just have one too many. We've got 10 edges, so there's no way this can be a planar graph. So this is smaller than the size of our edge set. Therefore, K5 is not planar. got one too many edges. And so there's our proof that K5 is not a planar graph. So we tried to get some intuition behind that last lecture, and now we've given a formal proof that shows K5 is not planar, and in fact it has one too many edges, because we've already seen that K5 with one edge removed is planar. We got that through our intuition from last day. Now there's one thing worth noting here, and I'll put it as a warning, and it's how to read this result, or how to read the theorem from the previous slide. So the previous slide, this theorem says that if G is connected with 3 vertices or more and planar, so if it's a planar graph, then this has to be true of its edge set. It can't have too many edges. If it's planar, then the edges are bounded. It does not say if the edges are bounded, then it's planar. The reverse doesn't hold. If the edges are bounded, that does not imply it's planar. And so that's worth noting, because that's often a trap that people fall into. So warning, the converse of the theorem is not true. Having the number of edges less than or equal to 3 times the number of vertices minus 6 does not guarantee the graph is planar. And so here's maybe we'll call it an exercise. Give an example of a graph with the number of edges less than or equal to 3 times the number of vertices minus 6, but is not planar. So it does have the edges bounded by 3v minus 6, but it's still not planar. And here's my hint. We really only know of 2 non-planar graphs right now. We know K5 and we know K33. We've just worked out K5, and we found that the number of edges is bigger than 3v minus 6. So that won't be our example here because it doesn't satisfy this statement. But what about K33? K33 is not planar. How many edges are there in K33? How many vertices are there? Well, K33 has 6 vertices. So 3 times 6 minus 6, that's 12. So in order to satisfy this inequality, we just have to have the number of edges being less than 12. Are the number of edges in K33 less than 12? Yeah, they are. And so it does satisfy this inequality, and it's not planar. So even though it's got a small number of edges, it still isn't planar. So hint, think K3, 3, because that's the only other non-planar graph we know about. Okay, so we know it's non-planar from last lecture just because it was one of the facts that we were using. But now it's time to prove it. So let's actually prove K33 is not planar. What this tells us right here is that this previous theorem alone is not enough to tell us that K33 is planar. So this previous theorem, this one, it's not enough. It's not enough. It actually turns out that K33 satisfies this identity. The number of edges is smaller than 3v minus 6. So we're going to have to do better to try to show that it's not planar. Well, what do we know about K33? Well, it is triangle free. There are no cycles in it of length 3 or less. So maybe we can use that to our advantage. So I'm going to write that down, that this statement here, with no cycle of length 3 or less, this is what we call triangle free. Because we're thinking of a 3 cycle as a triangle. So if we've got a connected planar graph with 3 or more vertices and it's triangle free, then the number of edges has to be bounded above by 2v minus 4 in this case. Let's see why that's the case. So since G is triangle free, each cycle has length at least 4 now. There can't be any 3 cycles. So each cycle has length at least 4. Also, since the number of vertices is bigger than or equal to 3, then we are out of these simple cases where we've got just, two vertices and an edge connecting them. There has to be more to our graph. That's really what the vertices being at least 3 means. It's connected with at least 3 vertices. It means there has to be more to our graph. And so that means that we have the degree of a face is at least 4 for all faces. So because it's triangle free, we can't have just a cycle of length 3 going around a face. There's got to be more to what's going on around a face. So each face has to have degree at least 4. And so now we're just in the same situation as we were with the last proof. It's just now we have a 4 here instead of a 3. So we go through the exact same proof as we did before. So by theorem 6.3.3, which is the degree sum formula for the faces, we have that 2 times the number of edges is equal to the sum of the degree of the face as we run over all the faces, and these are at least 4 each, so that's 4 times the number of faces, or in other words, we get that the number of edges dividing through by 2 is at least 2 times the number of faces. So that's the second one that we've just proven now, so that's worth noting. What else do we know? Well, we know by Euler's formula we have that 2 is equal to the size of the vertex set minus the size of the edge set plus the size of the face set. And so the faces we know are less than 1/2 of E. So we can replace, maybe I'll put it in a different color. What I'm doing is I'm saying, hey, that size of F there, that's less than 1/2 E by that result. So let's simplify this a little bit. I get 2 is less than or equal to V minus 1/2 E. We're bringing E over to the other side. I get E is less than or equal to 2V minus 4. And so there is our inequality we want. So that tells us that for triangle-free connected planar graphs, the number of edges cannot exceed 2V minus 4. Let's see what that tells us in this case. For K33, the size of the vertex set is 6. The size of the edge set is 9. And so what is 2V minus 4? Well, that would be 2 times 6 minus 4, or 12 minus 4, or 8. And that is smaller than 9, which is the size of the edge set. So the edges, there's just one too many in order to satisfy that formula. We're just one more than what the formula is telling us. If it's to be planar, then we have to have at most 8 edges, but we've got 9. And so since K3 is triangle free and does not satisfy the number of edges less than or equal to 2v minus 4, then K3 is not planar. And so we've proven that K3 is not planar. Again, we have the same warning. This condition on the number of edges is not sufficient to guarantee planarity. It is a necessary condition for planarity because if the graph is planar and triangle free, then it's necessary that this inequality has to hold. But just knowing that this inequality holds is not enough to guarantee planarity. So again, we'll leave this as an exercise. Find a graph G which is triangle free and non-planar, but doesn't have too many edges, but satisfies the number of edges is less than or equal to 2v minus 4. Let's try to come up with a graph that does that. And much like the other one, I'll give you a hint. So we only know a couple of non-planar graphs, K5, K33. We've already exhausted those ones in terms of the kind of edge bounds that they have. But the thing to note with K33 is we could subdivide it and still have a non-planar graph. Same with for K5. We can subdivide it, still get a non-planar graph. What happens when we subdivide a graph? Well, we add an extra vertex, so the vertex count goes up by 1. And the edge, we remove an edge, replaced by 2. So the edge count goes up by 1. So when we subdivide a graph, we bump up the vertex set by 1, we bump up the edge set by 1. So now if I look at this inequality and I say, what happens when I bump the edge set and the vertex set up by 1? Well, this side would go up by 2 every time, but this would only go up by 1. So if I started with a graph where the number of edges was bigger than 2v minus 4, then I could just keep subdividing. And I would bump this thing up by 2 every time, and this one only up by 1. So eventually the right side would pass the left side, and I'd construct an example for which this inequality was true. So again, maybe being a little bit more brief, hint, subdivide a known non-planar graph to come up with this example. Right, I'm interested in finding a non-planar graph which satisfies an inequality. So start with a non-planar graph and subdivide it until you get it satisfying that inequality. All right, so now we've shown that K5 and K33 are non-planar. We've also got a couple of properties that planar graphs have to satisfy. So now I want to introduce one more idea for planar graphs, and this is this notion of a dual graph. So I'll draw it first, and then we'll go through the definition of above. So suppose we have a planar graph, and we've drawn an embedding of it. There's an example. Then from this graph, we can construct a new graph where the vertices of my new graph are the faces of this graph. So what I'm thinking of is, instead of labeling F1, F2 as the faces, I'm going to just drop down some vertices right on top of those faces. And now I'm going to construct a graph with these as the vertices. And this is going to be the dual of our graph G. What are the edges going to be? Well, I'm going to connect two vertices by an edge if there's an edge on the original graph separating the faces that those two vertices are on. And so if I look at these two vertices in pink, there's an edge that is separating the two faces they are on. So I will add an edge that crosses that. But here's another edge that's separating this face and this face. So I will add an edge. And then there's another edge that's separating this face and this face. So I will add an edge. And this is called the dual graph, which we call G with a star as a superscript. And that's what the description up above says. Let's have a look at another example. So we'll look at an example with some loops and some parallel edges. Maybe something like this. And so there's our graph. We'll call it H in this case. And now we'll drop down the vertices for my dual that are going to be right on the faces of H. So there's 4 faces, so I've got 4 vertices in my dual. And now I'm going to construct edges for my dual graph. So this is going to be my dual graph in pink. What are my edges going to be? Well, I'm just going to connect 2 vertices if they're separated by an edge in the original graph. So those 2 vertices have an edge separating the 2 faces they're on. These ones do. This edge is the one separating these 2 vertices. This edge is the one separating these 2 vertices. So all I'm doing is I'm making sure that I cross every edge. So for every edge in the original, I'm going to introduce an edge in the dual that connects the 2 vertices on either side of that edge. So the 2 faces on either side. So then I'm going to have to connect it by an edge. And what about this edge here? Well, it separates the face on this side and the face on this side are actually the same face. And that's the face I attached to that vertex. So that means I have to have an edge that comes around like this to make a loop. And so there is our dual graph H star. Now the reason we've defined it this way is the following. If I think about a corresponding vertex in my dual, what is the degree of that vertex? Now it makes sense to talk about the degree. It's just the number of edges that are coming out of it. And so this vertex has degree 3. So that's degree 3. But notice that's the length of the facial walk around that face. What's the degree of this vertex? It's degree 3, but that's because it's the degree of the facial walk around that infinite face. What about something like this one here? What's the degree of this vertex? Well, that face has degree 1 in H, and so in the dual graph, it's got 1 edge leaving it, so it's got degree 1. And so that's just the observation we can make about how our definition works. And so what we have is the features of this dual graph is that dual graphs only exist for embeddings of planar graphs. If G star is the dual of G, then G is the dual of G star. That might be kind of clear from how these diagrams were drawn, is that if I did the same thing, if I took G star and then found the dual of it, I just get back to the original G. And similarly for the other one. So a dual of a dual is just back to the original. This was the one I was just talking about. The degree of a vertex in G star is precisely the degree of the corresponding face of G. And our second example shows that a dual of a simple graph may end up being a multigraph. So in terms of that point about the connection between degree of a face and degree of the vertex in the dual, let's just look at an example. So suppose our graph looks something like this. It's just a small portion of our graph. So this is G. So then we got this face of G, which has degree 4. So I'll throw a vertex down there. And when I construct the dual graph, I end up adding edges. One edge for every edge around the facial walk of that face. And so the thing to note is that this face has degree 4, and that's precisely the degree of this vertex. So maybe I'll say vertex has degree 4. That's really why we get the degree sum formula for the faces, because the degree sum formula for the faces, the sum of the degrees of the faces equals twice the number of edges, is really just the sum of the degrees of the vertices in the dual is equal to twice the number of edges in the dual. But because the number of edges in the dual is exactly equal to the number of edges in the original graph, we get that the sum of the degrees of the faces in our planar embedding is twice the number of edges. So it's really just following from the degree sum formula for the dual graph. And so the introduction of the dual graph is just something that helps us understand planar graphs, because we can often cast questions about the planar graph into questions about its dual. One thing to note though is that the dual is specific to the embedding. So if I have a graph G and I embed it as a planar embedding and construct a dual, if I took a different planar embedding, I could get a different dual, something that is not isomorphic to the dual of another planar embedding. So different planar embeddings can give rise to non-isomorphic dual graphs. That's just something to be aware of, so that when you're talking about a dual graph, it's specific to the planar embedding, not specific to the graph itself. It's the planar embedding of that graph. All right, let's have a look at our application of these ideas to Platonic solids. So here's 5 Platonic solids you've probably come to know and love over the years: tetrahedron, hexahedron, also known as the cube, octahedron, dodecahedron, and icosahedron. Turns out these are the only 5 Platonic solids. Now, what does it mean to be a Platonic solid? It means that your faces are made up of regular polygons. So in this case, triangles, squares, or pentagons. And there's the same number of them coming together at every vertex. So for our tetrahedron, we have 3 triangles coming together at every vertex. For the cube, we have 3 squares coming together at every vertex. For the octahedron, we have 4 triangles coming together at every vertex. For the dodecahedron, we have 3 pentagons coming together at every vertex. And the icosahedron has 5 triangles coming together at every vertex. So that's what it means to be a Platonic solid. We've got also the connection with graphs down below. So these are representations of just the vertices and the edges of our Platonic solids above. One way to think about this is if I take this cube and I puncture it here and sort of then pull it back and unfold it or squish it down onto the plane, then I've essentially taken this top square and just pulled it around, kind of like rubber, pulled it around and then pushed it down onto the plane. You can do the same thing for the other shapes as well. You can puncture the middle of one of the faces, pull it open and push it down onto the plane. Similarly for the pentagon and the icosahedron. In all cases, the face that you puncture and then pull apart and lay down in the plane is that outer one here. So these are nice representations of these objects as graphs. Now what can we do with this? Well, we can extract from these planar graphs the common properties. So we'll consider a planar graph with each vertex of degree n, which we'll say is greater than or equal to 3. So they all have the same degree. So whether you're in the first graph where they all had degree 3, or you're in the last graph where they all have degree 5, the idea is that you've just got a graph where each vertex has the same degree. So we call this n regular graph. If all vertices have the same degree, namely n, then we call it n regular. So consider a planar graph with each vertex of degree 3 and each face of degree m. And again, that's greater than or equal to 3. So this is just going to be, in the first case, our faces all have degree 3, including the infinite face, it's a degree 3. Or in the case of the cube, every face has degree 4. Or the octahedron, every face has degree 3, and so on. So I'm not making any assumptions about these values. I'm just saying every vertex has degree n, and every face has degree m, because that's a common property that all of these graphs have. And we're going to show that in this case, there's only 5 choices we could have for n and m, and they represent these 5 graphs. So by the degree sum formula, what do we have? Well, we have that the sum of the degrees of the vertices is twice the number of edges. And the other degree sum formula, the sum of the degrees of the faces is twice the number of edges. But in the first case, every vertex has degree n, and so this is n times the number of vertices is twice the number of edges. But in the second case, every face has degree m, so this is m times the number of faces is twice the number of edges. And so we get these 2 results. By Euler's formula, what do we have? Well, we have 2 is equal to the number of vertices minus the number of edges plus the number of faces. But we can use these 2 expressions to rewrite the number of vertices in terms of the number of edges and the number of faces in terms of the number of edges. So what is v? v is 2 over n times the size of e minus the size of e plus the number of faces is 2 over m times the size of e. So now I can write this as, well, I can factor out an e mn from each term. And so for that first one, I get 2m. For the second one, I get mn. And for the third one, I get 2n. And now at this point, the crucial observation to make is the following. I am adding m and n together, basically twice them, so 2m plus 2n, or twice of m plus n. And then I'm subtracting off their product. Now these are integers. Both m and n are positive integers. They're each greater than or equal to 3. When I add 2 integers together, they don't grow nearly as fast as multiplying them. So I expect this to be much bigger than this. The problem is that would mean that this expression would be negative. But it's not negative because everything else in it is positive. So because this thing is supposed to be positive, it's telling me that there's not many solutions to this. There's only a few m and n values for which this is going to be positive. So let's go ahead and look for those. So this tells me that 2m minus mn plus 2n has to be strictly positive. But then if I negate both sides, then what I get is mn minus 2m minus 2n is strictly less than 0. I'm going to add 4 to both sides of this. You might say, why are you adding 4 to both sides? Well, the reason is now I can recognize this left side as a product. It's m minus 2 times n minus 2. And that's got to be less than, strictly less than 4. And this is what tells me what m and n have to be in order to solve this. So what are our solutions? Well, our solutions could be m is 3 and n is 3. Remember, both m and n have to be at least 3. So they could both be equal to 3 and satisfy that. So n is the degree of a vertex. So that's how many things are coming together. M is the degree of the face. So that's the kind of shape. So this says we've got M is 3, so there's the shape is a triangle. And we've got 3 triangles coming together at every vertex. So that's a tetrahedron. So this solution corresponds to a tetrahedron. What's another solution? M is 3 and n is 4. Then I get 1 times 2, and that's certainly less than 4. So I can get an m equals 3 and an n equals 4. So those are triangles again, but 4 of them now come together at every vertex. So what is that? Well, we can always look back up here. We have now triangles, but 4 of them are coming together. That's the octahedron. That has 4 triangles coming together at every vertex. So this is our octahedron. What else can we have? We could have m equals 3 and n equals 5, because that would be 1 times 3. That's still strictly less than 4. So that's triangles, but 5 of them coming together. That's an icosahedron. And that exhausts all the cases with triangles. So then we can go up to squares now. M equals 4. And if m is 4, then looking at this expression here, if m is 4, then this value is going to be 2. So this can't be any bigger than 1. So that means n has to be 3. So we get n is equal to 3. So that is squares, 3 of them coming together at every point. That's our hexahedron, also known as a cube. And then what's our last one? If m is 5, then n has to be 3. So m is 5, n is 3. So these are pentagons. So we've got pentagons coming together, regular pentagons. There's 3 of them coming together at every vertex, and this is going to be our dodecahedron. And that's it. There's no more solutions, because if m was bigger than 5, then this inequality wouldn't work. And so we got 5 solutions to this, and therefore 5 Platonic solids. So there's an application of Euler's formula and both of our degree sum formulas that all came together to prove that there are exactly 5 Platonic solids. And that's interesting because this is a question about planar graphs, but we've actually used it to prove that these are exactly 5 3-dimensional objects with certain properties. So we proved a result in geometry using results about planar graphs. All right, so that's it for this section. Thanks very much for watching, and we'll see you again next time.